I want to introduce Professor Haskell because Dick has been with us for the last 4 years, and he's going to share with us a little bit about his own personal journey with this that might resonate with a lot of you. So please welcome Professor Haskell.
First of all, I want to welcome you to Harvey Mudd College. This has been my home for 37 years. I just hope you enjoy it as much as I did. It's been a great place. So it's a particularly satisfactory situation to see the clinic team launching into a test of really a field test of this new technology, which is just part of this, amazing CLGP program. And this is a bit of a confession, but it has an interesting twist to it. I remember about a year ago, or maybe 6 months ago, as I was really coming up to speed on this idealPV technology and the patent. And so my reaction to hotspots, which are indeed a serious problem, but I had never heard of them before. And the solar industry is such a mature industry. I thought, really, hotspots? I mean, they're a problem, but I have had solar panels on my roof since 2001. And so I was just unfamiliar with this and being skeptical but curious. I'm a scientist. I was very curious, but I look back now and I think, boy, I was really skeptical. As it's turned out over the past 6 months or so, slowly I and the team and other faculty involved in this operation here on campus slowly began to realize that there's just been no talk about it. It's one of these, it's the 500-pound gorilla that's sitting in the room, no one's talking about it. I think Peter Saita over here is now director of the physics clinic program, finally found an old book, well, it's a 1990s book, by a very famous solar physicist from Australia. And in his book, he said, hotspots are a problem. They can be mitigated with bypass diodes. If you've ever heard of bypass diodes in the solar industry, that's the current technology that's typically used to protect solar panels against hotspots. But the word he chose was mitigate, and I've seen that word repeated throughout the literature, which has been recently amazing, and we began to notice that there are papers appearing. They started to appear roughly in 2010, just conference papers and so forth. And then finally the big IEEE, that is the IEEE journals, which is the electrical and electronic engineer journals, the very top journals, are beginning to come out with papers that are describing hotspots, and they're now saying, hotspots can be mitigated by these bypass diodes, but actually there still can be damage done by these hotspots, and there's still a problem. And so we have, then the introduction to the paper is we're trying to find a way to detect when hotspots are about to burn up a piece of the panel. And then finally, as the years go by, as we look in the literature and begin to dig out more, we realize that people are now saying, well, we're offering a way to detect and prevent. Well, if you look at the papers that say they're going to detect and prevent, they actually don't get quite around to saying how they're going to prevent it. And so we have realized, to make a long story short, we have realized, and I'm feeling a little guilty about this. I was so skeptical initially, but I must say that as we look at the literature now, suddenly this has become a hot topic, but it really is. And the papers are coming out so rapidly. There's one that just came out in January 2018, so we really have to stay on top of this. This is an opportunity that we really need to take advantage of. And Kent and the guys from idealPV have really put their heart and soul into this, and I think we're going to be the beneficiaries of it. So thank you for that. And welcome to Harvey Mudd, and let's hear what Kent has to say about his technology.
You know, in the turn of the century, every house was different, and it was the best houses were made out of kiln-dried lumber, and everything was perfectly square and pre-shrunk, and it was great. And so the idea was that if you could get to the completely perfect construction technique, you'd have the perfect house, and only super rich people could have that perfect house. Very few of them. Everybody else had wind blowing through them and caulking and chalk that fell off between the logs, and it was a mess. But today everybody can have a house, at least can live in an apartment that has walls that seal, and the lumber is green, and it doesn't matter. We've standardized all our construction techniques, and we're tolerant of being able to do a mass production technology in housing with the materials that we have. We've adapted the practices that we have for construction to meet that. Now, we would like in solar for there to be no shadows, no impurities, nobody mishandles the solar panel, the temperature stays constant, but that's just not how it is. Let's see, is there a button that points? This big one? Yeah. And we would like the people that install them to do everything perfectly so they don't actually, at no time of the year will they ever shade one another. So we've got this vision that, we can make it really perfect. But even if you clean them all the time, this is an array I owned, but you can see actually the dust gradients just, over a few months. And they're not uniformly distributed over the solar panel either. It's just really hard to make things perfect. This is rain splashing up off of a roof and then picking up the dirt on the roof and then redepositing it down on the bottom of the solar panel. And the solar cell is supposed to go down here. Nobody probably even saw it. It was above the building parapet, right? So, and then in my part of the country, we get this. And it seems to preferentially treat the solar panels too. So we wouldn't like that stuff to happen. So in the solar industry, we just like not to have all this stuff. But the reality is, if we want to do a mass deployment, not only do we have to deal with this, but we have to deal with all the households, whether or not there are trees, chimneys, mistakes in the installation. We want to try to take as much advantage of the rooftop as possible. So we can't drive the environment to be perfect. We can't eliminate the birds. We can't eliminate the defects in the silicon. And it turns out that it's a big deal. So, yeah, that happens. These things get so hot that they melt their own internal plastics, or sometimes more, like unsolder a solder joint on a high voltage DC connection, which then results in an arc. And this particular one, that particular one, I think it was in Coffin Bay, Australia, but this happened all over the world. It took out a building the size of a city block in Germany. Our latest electric code revisions were because of Dietz and Watson warehouse facility in New Jersey burned to the ground 300,000 square feet while the firefighters watched because fighting it would be dangerous because of the high voltages involved. Best just make sure the installations are only those perfect ones. So today we only have solar for the perfectly sited southern roof in general. We don't really want to do, when you say, let's do half the households, all from the lowest income to middle income, all 6,000 of them, whether or not they're perfectly solar sited, that's not okay. That would actually violate the warranty terms of the solar panels. We're not even going to do that. Michael is here, and he did an analysis of how much solar resource is actually available in terms of the rooftop in Claremont. I believe it was about 30% is installable. And I bet you that doesn't line up with half the population that's low and moderate income either. So that's a problem. You really need to be able to take it as it is, and you can't have these risks at large scale deployment. So that's where we are on the cusp of, we want to solve the climate change problem. We've got a technology that lets us use the current account of solar radiation coming on the planet. We don't have to use this ancient stuff that was buried a long time ago and then burn and release that energy. But it needs to work for all the houses. Just like when we went at the turn of the century from that hewn lumber to green lumber. So this is a real-world test stand, one of the two trailers that is actually parked right out here on, I used to know the name of that field, the athletic field just over here to the east, Lind Field, northern part of the field. And what this represents is the fact that we're going to install on at least 2 roof faces. The houses aren't necessarily squared up north, south, east, and west. Many of them will be actually 3 roof faces because the house is not that many square feet and we're looking for more resource. We're going to use all the installable space, whether or not somebody put a vent pipe that shadows it part of the time, or a chimney, or a tree. Trees are kind of important in Claremont. We don't want to sacrifice that for solar. So this is a test stand that actually represents sort of the average thing that we're going to have to do when we install these on all the rooftops, not just the perfect ones in Claremont. And it's important to recognize when we talk about efficiencies and yield in solar, the yield from a rooftop you didn't install is 0. So you want something that works in the perfect ones and the imperfect ones alike. Now these are standard solar panels. They happen to be the very best that we could find. They're very top of the line Kirsch. They're very high efficient cells. These are idealPV panels, and you'll see those on the trailer. And we did a couple of things just to make sure that we were really modeling what's going to happen in the factory, and the clinic team just found out about that for the first time today. So we actually took the step of making these out of silicon that is lower efficiency silicon. And the middle solar panel is made out of an entirely different technology, lower efficiency silicon. So we have some solar cells that are kind of mid-grade efficiency but still lower by a point or more, which is a big deal in solar. And then we actually have some just sort of random eBay cells that we got that are 2 bus bar cells. And in addition, idealPV panels are meant to be easy to make. So not only are these cells, made out of these quarter pieces, because that allows us to throw away the ones that are chipped in the corners by cutting them into 4 pieces and just keeping the good parts. But also the spacing in between the individual cells is much larger and more generous, so that alignment when people are actually doing this instead of robots is easy to do. So we couldn't fit as many. So these actually have about 4% less silicon. So you have less silicon, it's lower efficiency, and the whole system is set up in real world conditions, and guess what? It still produces much more power than the original panels. A vent pipe like that will cause hot spots in excess of 400 degrees in these traditional solar panels protected by bypass diodes. And just on a middling day, 2 days ago, we were measuring 200 degrees when it was partially cloudy and we had the rainstorms going through. The backskin rating on this particular panel is just a shade over 200 degrees Fahrenheit. Let's talk about how this hotspot thing really is today. So this is a third-party simulation of what's going to happen, what happens with hotspots of various shading. And one of the things that's important is the UL 1703 test that we have that's supposed to make sure that these solar panels are safe. It's based on shading half the solar cell. But we know when we look at what happens with birds and leaves and stuff, the shading is random. It's not big chunks, like a 3 by 6 inch chunk that's half of a solar cell. Sometimes it's just something the size of a quarter. Well, guess what? That actually results in even higher temperatures. These are in Celsius. So they're talking about temperatures exceeding 200 degrees C. William was just here when they did the testing in Pomona. I believe they were reaching temperatures that were about 180 degrees C in the laboratory with 20% shading here at Pomona College. So anyway, the worst case shading is about a quarter, but UL 1703 is 50% shading. Okay, we'll take that. So that's the quarter test. That is a human finger because the quarter is right there. That's the cool spot the quarter made on an idealPV solar cell or on a solar panel made with idealPV technology and solar cells of middling and low quality. So the basic thing you're seeing is in the limitation of the resolution of the camera, we can't see that. Now that's the hot spot that's supposed to cause, does it go backwards? That button. These temperatures. But it didn't. In fact, the net power loss for the whole solar panel was less than a couple of percent. So not only did it not get hot, it didn't actually make much of an impact at all in the production of the solar panel, even though that was actually shading roughly 7% of that little cell. This is a UL 1703 hotspot type test. Shaded half the cell. These are actually one of the very panels that are out there. Set it up normal to the sun. We found the hottest cell and we shaded it. TSR panels, 286 degrees Fahrenheit. So way, way over about the 210 degrees that this particular backskin is rated for. That should have failed UL 1703. That's been one of the interesting issues we have in the solar industry is our cells have gotten more efficient. The hotspot problem is getting worse. And the standards have stayed at this level. And we're deploying now solar panels that appear to be actually marginal or stepping way over the line in terms of material safety. But that's happening. And it's a pretty easy test to do with a piece of foil and a light meter and an infrared camera. In that same test on the idealPVs, the solar panels actually had net cooling in that cell. Okay, let's look at what should be happening when we have these arrays that are pointed different directions. What should be happening is they all add together and they actually just make essentially a somewhat longer solar day with a lower peak. That's what we expect to have happen. The clinic team actually did this based on, I believe, climatologically adjusted data and came up with the fractions that they expect in terms of efficiency. The problem with the conventional solar panels is they're going to put a large fraction of that power back into heating themselves up instead of actually producing power. And the idealPV panels actually produce the power. So you end up with a much more efficient system. It's not just about trying to make the whole thing lower cost and make it manufacturable within the cities, but actually making a superior product in terms of energy yield that you can make locally in the cities with local workers and deploy on all the rooftops. It's just, I'm going to skip over the technology of this just to say the idealPV panels are really the first ones that are designed from the ground up about efficiency, manufacturing efficiency and power yield, and that's really the primary concern. And so once we took out the hotspot problem, we're able to re-architect the panels. Now, I think the colleges and the technologists are going to take advantage of this in ways that are difficult to imagine. But I just want to leave you, before I get off the slides and the prepared remarks, with just this vision. This is the solar technology that we use today in the solar industry, and we're stuck. Wafer scale, about 6 inches, about 1985 semiconductor technology. This is the technology that we use to make the watch and the chips in your cell phone today. 18-inch technology. We can't make a solar cell that way because we can't do chip scale kinds of technology in solar in traditional solar panel architectures. In idealPV panels, we use them in chip form just like your watch does. And so right now, the solar industry is struggling to make cost-effective material at wafer scale when all of microelectronics has moved on for decades into chip scale, very large scale fab. In addition, a lot of the innovations in solar, in anti-reflective coatings, in dye-sensitized solar, they use organic materials that really have no hope of existing over 100 degrees C. And so these things are laboratory curiosities that we can't really hope to deploy with today's hotspot environment that now get unleashed. And so if you look at the idealPV technology as it is today, that is a bridge to what the future is, using today's technology, the chips, the cells that we can get available today, rejected and otherwise. But when we get about the technologists at Harvey Mudd and in Pomona College with their prototype facility, designing cells where hotspots aren't an issue, it's difficult to imagine how much more efficient and how much more low cost those cells will be when they're designed for this kind of an environment. The guys that were building those cabins at the turn of the century with those perfectly hewn square beams that they dried in a kiln looked at what they have at Lowe's today to throw together a roof and a rafter set, they would be amazed that there would be standardized hardware like that. So I think if we look back at this in a decade, we'll be amazed at the leaps that we took in solar technology, just employing the anti-reflective coating on these glasses, which would vaporize at the hotspot temperatures that we have today to improve the light efficiency of solar cells. So this is really only the beginning of a technological revolution in cost-effective, manufacturable, mass deployment solar. Very, very exciting time. Okay, and that's going to be it. The world's first community solar panel factory.